Last time, we went over why you might want to use embedded Linux, and I showed you how to create a quick custom Linux image using Buildroot. This time, we're going to create another custom image, but we're going to do so using the Yocto project instead. Let's dive in. Before we look at the command line, let's take a moment to review some terminology, as it can get a bit messy. First is the OpenEmbedded project. This is a community-driven project founded in 2003 to create a suite of tools to help people create custom Linux distributions for embedded devices. The Yocto project was started in 2011 as an official Linux Foundation project. It relies on many of the tools and reference files created by the OpenEmbedded project, and OpenEmbedded is one of the collaborators in the Yocto project. This is why you will see many files with the OpenEmbedded or OE prefix when working with Yocto. The Yocto project tries to maintain support for a number of popular architectures like x86 and ARM. The OpenEmbedded toolset calls any files used to configure the build process metadata. These can be things like settings or source code locations. A recipe is a specific type of metadata used during the build process that contains instructions on where to download source code, configure it, and compile it. The build system groups metadata together into layers, which are nothing more than directories that contain the metadata files. Most layer directories begin with the meta-prefix, although that's not always the case. A board support package is a special type of layer that defines how the build system should configure things for a particular board. It might contain recipes for downloading and compiling drivers unique to that board. BSPs are often maintained by vendors. If you are creating your own single board computer or module and want to have support for it in the Yocto project, you will need to create your own board support package. A distribution is a specific implementation of Linux, much like Ubuntu, Fedora, and Arch Linux are all different distributions. By using these tools, you are creating your own distribution. The machine configuration refers to the physical architecture and board that the system should build for. It usually points to a specific board support package to assist in this process. An image is the output of the build process. It contains the custom Linux distribution you just built, which includes the kernel, any necessary boot programs, drivers, packages, and the root file system. You'll often flash the output image onto an SD card or other non-volatile memory on your board. The official Yocto project documentation has this great diagram showing how the build process works. We configure any necessary metadata, which the build system reads to figure out where to download the necessary source code. It applies any sort of patches required, tests the generated packages, and creates the output image or images. You might get more than one image depending on your settings in the metadata. The variety of images give you options in setting up different boot chains or choosing different file systems. You can have it generate a software development kit to make writing code for your particular board easier. Note that creating board support packages and software development kits is a lot of work that we won't get into in this series. The idea is to get you used to working with the Yocto project to create your own images and begin writing code for your custom distribution. If you did not do it in the first episode, you'll need to update your package manager, and then you will also want to run upgrade in order to upgrade all of the necessary packages. This can take some time if you haven't run it in a while, so just be patient with it. So then after running apt update, we'll run apt upgrade. This will cause your package manager to upgrade all of the packages. Say yes if asked, and wait a little bit of time. While it's doing that, I'd like to point out in the Yocto project reference manual, there is a list of supported Linux distributions. These are the Linux distributions for the host machine that have been shown to work with the Yocto project. You're not necessarily required to run one of these, but it's highly recommended because they come with known good packages and they've been tested by the Yocto project community. I would normally say go for something like Ubuntu, one of the long-term support distributions. However, I am running Linux Mint because, I don't know, I like to be different and the machine that I'm running it on is low power. You will also need about 50 gigabytes of free space. I would say at least 50 gigabytes of free space on your hard drive, and I would say at least 4 gigabytes of RAM. This poor machine only has about 2 gigabytes of RAM, so we're gonna have to trick Yocto to work with that, and I'll show you where to do that. In order to run the tools in the Yocto project, we will need some packages and tools that are dependencies. I recommend using apt or whatever package manager you have to install the following. You will probably want to look at the Yocto project reference manual to get an idea of what else you need to install. As you can see, I already have these installed, but for you, you might have to wait a little bit to install them. The other thing that I found is that specifically for the STM32MP1 build process in Yocto, you will need the development version of the SSL library. And that is for some SSL packages that they require you to use when building it. If you just try to type Python, it will not work, and that's because Python requires you to use either Python 3 or Python 2. And since we installed Python 3, we can alias the term Python or the command Python to that. So use something like VI or whatever text editor you want. In VI, scroll down to the bottom, hit I, and then we're going to type alias Python equals Python 3. So now when I type Python, it will execute Python 3 instead. Hit escape, :WQ to write and quit. And then we're going to call source on that -rc file so that we run it again. And now when I type Python and spell version correctly, you can see that it will run Python 3, in this case 3.8. From my home directory, I'm going to go into that projects folder that I created in the first episode. All I have in here is Buildroot, so we're going to put Yocto Project next to Buildroot, and we are going to download the Pokey reference distribution using Git. When I say that Pokey is a reference distribution, Pokey is not Yocto Project, and Yocto Project is not Pokey. A reference distribution is all of the metadata, layers, board support packages, bitbake, and various other tools that make up the Yocto Project, or even OpenEmbedded, where it will generate various images in a known good fashion, and that's our reference distribution. So Pokey is a good place to start when you're working with the Yocto project. Using Pokey, we can then add our own layers to create a customized version of our own distribution. Once Pokey has downloaded, go into that folder and you can take a look at what's going on in there. Bitbake is our main tool that we will be using to read in the metadata, the recipes, the board support packages in order to create our custom distribution and generate our images. All of the meta-pokey, meta-whatever folders, those are our layers. They consist of various metadata that is used by the bitbake process. You can also look at the various scripts and documentation that comes with this, but those are the main folders that we need to be concerned with. When working in the Yocto project, you will want to make sure that all of your branches of your various repositories match. To start, I recommend looking at what's available for the various Yocto project releases, and these should line up with what's available in the Pokey reference distribution. Generally, you'll want to look for long-term support, which are supported for at least 2 years. The big thing to pay attention to here is the code name. This aligns with a specific Yocto project version, and everything we do whenever we download layers from other vendors or board support packages, you will need to check out the version that lines up with this code name. If you have a mismatch between the Yocto project version and your various layers, you will likely find that things won't compile or build correctly, so you have to pay attention to this. We will be using the ST Microelectronics Meta ST STM32MP board support package. This whole thing is a board support package that ST has created in order to support their various single board computers or reference boards or evaluation kits. For our purposes, the STM32MP157D-DK1 is supported in here, and it allows us to import all of these files into the Yocto project supplementing the Pokey reference distribution, and then creating a custom Linux build. The important thing here is to look at the various branches. These names should line up with what you saw available from the Yocto project releases. And this is going to be the case for nearly every vendor that has its own board support package. Regardless of which board you're using, you will want to read the vendor's documentation to figure out how to include the board support package. This is, of course, assuming that vendor supports the Yocto project. So here we have Dunfell, and this seems to be the recommended branch, the default branch for this particular board support package. If we go back, Dunfell is indeed the long-term support release for the Yocto project, and we need those to line up. If you include other layers, maybe things that have security, or you find something that has graphics drivers for your board and it's not part of ST's board support package release or something else that they have done, you will also want to make sure that it has the Dunfell release when you go to check out a specific repository branch. So once we're done confirming that all of the releases line up, we need to make sure that we check out the releases for every single layer, including the Yocto project itself, or the Pokey distribution. Calling git branch will show us the local available branches. That does not look like Dunfell is a part of that. In this case, we can call -r with branches to see what's available. And you can probably find Dunfell in here, so you can see origin and the various names that are available. So I can scroll down, and sure enough, origin Dunfell is available as a branch, which means I can just call git checkout Dunfell, which is the name of that branch or release. Once it's checked out, you should be able to call git status and see that you are on the branch Dunfell. Once you've checked out a particular branch, I recommend looking at the distribution config file in order to see some information about it. At the top, you should see that you're working with the Pokey reference distribution. We are working on the Dunfell branch, and that should line up with any layers that we will download in the future. If you scroll down, you should see a variable listing the Sanity tested distributions. These are the distributions that this particular reference distribution was built on, so your host machine. They built it on a few versions of Pokey, as well as things like Ubuntu and Fedora, as well as a few others. If you are not working in one of these distributions for your host machine, you will probably get an error. That does not mean it won't build. Since I'm working on Linux Mint, I expect to see an error. If you're doing this on your own, I do recommend using one of these distributions when you go to build because they're known to work. But I like to be different, and we'll see if everything works. Although that's a bit of a lie because I definitely tested this earlier and it does work on Linux Mint. The Yocto project, specifically Pokey distribution, does have some support for a couple of things like BeagleBone Black, but a lot of times if you're working with something that's not supported by the reference distribution, you're going to have to download it from the vendor site or their GitHub page. The next thing that we're going to do is download our board support package from the vendor. Specifically, we're going to download Meta ST STM32MP. Notice that STMicroelectronics also maintains this reference Linux distribution for their boards, the Meta ST OpenST Linux. This is another layer you can download in addition to that board support package if you want to build their version of OpenST Linux. However, we are not going to build this because it contains a lot of things like Qt for doing graphics and things that we're just not going to concern ourselves with, at least right now. We want to build the bare minimum Linux, and to do that, we're going to use the Pokey distribution in order to make that happen. The OpenEmbedded project also maintains a list of known good layers that you can also import if you'd like. If you head to this layer index on their site, you can find these layers that are listed. Note that most of them are board support packages that have been created by various vendors to support their reference boards or development kits. However, you can find some other things that include maybe some networking or security type applications or packages for you to use. I'd like to point out that ST also has a workshop for the STM32MP1 that dives into some more specific utilization and how the hardware works on the MP1 series. We won't go into a lot of this, so if you'd like to learn more about the MP1, I highly recommend checking out this YouTube series in order to do that, as it will help you get started, say, creating your own board support package or creating a custom board around the MP1 microprocessor. But we're just going to be working with the development kit in this series just to get you familiar with working with Yocto Project in general in order to create custom Linux distributions. From there, let's go back to our host machine. Whenever I download new layers from third-party sources, I like to put them in a folder on the same level as the Pokey reference distribution, as that contains its own suite of layers. We're going to use Git to check out that STM32MP board support package layer, and now that layer exists on its own at the same directory level as Pokey. We want to go into that directory, and we want to check out the Dunfell branch just like we did with Pokey. Because it's default, it should say we're already on Dunfell, and we can run git status to verify that, yes, we are on the branch Dunfell. Dunfell needs to line up with what we saw in Pokey. Feel free to look through some of the recipes and layers that are in this board support package. You can also read the README, which is always a good thing to do. One of the big reasons to look at this README is so that you can figure out which other layers this board support package depends on. I have found that the OpenEmbedded core and BitBake come with Pokey. In fact, this is exactly why the README is saying you can download OE core or just use Pokey, which contains the OE core layer. So when we downloaded Pokey, these dependencies have been met. However, if we scroll down some more, you can see that the meta OpenEmbedded layer is also required. I hit page down, that's why it just jumped like that. So we're going to scroll back up, and you see that this is still part of the dependencies, which means that we need to download this meta OpenEmbedded from this URL. And we can copy this, and I'm going to quit out of less. I'm going to go up a directory to make sure I'm on the same level as these various layers. Then I'm going to clone that other layer. Once again, we go into that layer, and we want to check out the Dunfell branch. As you can see, we are on Dunfell, and we want to view the README to see if this has any dependencies. This is a very short README. As you can see, it's a collection of layers to supplement the OpenEmbedded core. It's going to be needed by our ST build, but this does not have any dependencies on its own. So hopefully we are done with downloading various dependency layers. Once again, we're going to go up a layer, and we're going to run this OpenEmbedded initial build environment that's found in the Pokey directory. This creates a build environment and does things like add BitBake to our path so that we can call it and any other tools that are needed. In addition, it will also create a build directory for us. The default name is build, unless we give it another argument. In this case, I'm going to call my build directory build-mp1, since we're creating a Linux distribution or build for this particular processor. When it's done, you can see that we're now inside the build mp1 directory, and we can list the files found in it, in which case there is not much. It's just a configuration folder. If you tried to run the bitbake command prior to running that source command, you will probably get an error that bitbake is not in your path. When we run source, bitbake is added to our path, so now we can call the bitbake tool. Another tool we can use is bitbake layers, and we can ask it to show the layers that are included in this build. As you can see, we have meta, meta-pokey, and meta Yocto BSP. When we create a bare bones Linux build like this, you will find that it's being built for the QEMU emulator, which is used to just verify that things are working, and it's just an emulator that runs on your host machine. But we want to build something for an actual separate single board computer, so let's do that. To start, we need to add the layers that we just downloaded, specifically the ST board support package and the OpenEmbedded layers. Inside the conf folder, you will find something called bblayers.conf. We are going to edit that. This bblayers.conf file contains some configuration about the layers that need to be included during the build process. The big thing you'll want to look at here is the bblayers variable. By default, this contains the various Pokey layers that are needed just to get a bare bones image built for that QEMU emulator. we need to add the required STM32MP board support package as well as its dependent layers in order to make this run. I'm going to go to the last line in that BB layers variable, and I'm going to push A because I'm in VI, but you're welcome to use whatever text editor you like. Hit enter, and let's write some lines to include that board support package. It will not be pokey. In fact, we need to point it to the other layers, and you should be using absolute paths just like the lines before it. Sometimes you can get away with pointing it to the top layer, such as the meta-OpenEmbedded layer. However, in this case, I found when I tried this, the build would fail, and I had to point it to a specific layer in that meta-OpenEmbedded. In this case, the STM32MP board support package wants the meta-OE layer inside that top level layer. The other layer that was required, when I tried the build process, it yelled at me because it was missing, was this meta Python layer that's also in the meta OpenEmbedded layer. And finally, we want to add that meta STM32MP board support package that we downloaded earlier. With that, I can hit escape, :WQ for write and quit, so save and exit. And then we can run that bitbake layers show layers again. It will spin up bitbake and show the newly included layers that we just added to that configuration file. The next thing we have to do is choose a machine that bitbake will build the image for. By default, it's building for that KMU emulator, so we need to figure out which machine to tell it to build for. You can kind of poke around in here to look for something like machine. So we'll go into that machine directory, and let's see what we have available. So it's a few configuration files. Let's take a look at that basic mp1.conf file. Doesn't look like there's anything particularly useful in here. Since I'm working with the DK one, which is the discovery kit or discovery board, let's take a look at that configuration file. You can look at those two configuration files to get an idea of what's needed. I'm going to go with this MP1 configuration file, which I believe the machine name is the STM32MP1. You can also see the exact layers that are needed here, which is where we're getting that meta-OE and meta-Python layers, rather than just trying to include meta OpenEmbedded. If you just try to include this top level layer, your build process will probably fail. So this is a good place to look to see which layers are required and specifically how to name them. You might be able to use the STM32MP1-disco as your machine name, but let's see if we can get it to build without it. You're welcome to try it on your own. To do that, I'm going to head back to that top level Yocto directory. And I'm going to head to my build mp1 directory. From there, you'll want to modify local.conf. This should be in the same directory as that BB layers that we just modified. There are a few things we need to change in here. Specifically, the big one is the machine selection. So I'm going to page down and you'll see where machine is set. I'm going to comment that machine line out, and I'm going to set a new one here for STM32MP1. Like I mentioned, you may want to try STM32MP1-disco to see if that builds and gives you a little more support, but let's start with bare bones for now. Something that I found I needed to do for my particular machine, because I only have about 2 GB of RAM, is to change how the XZ compression tool works. That's at the very end when it's starting to create the images and package all of the files together. It will try to grab 2 GB of RAM when it's running, and if it can't find it, it just fails. And we can pass arguments to specifically XZ by setting this variable. In this case, we're telling it to limit its own memory to 1500 megabytes, or mebibytes in this case, such that it will start to use swap space. Without this parameter, I found that XZ will just fail and not even attempt to use swap. And I have a lot of swap. I've got 8 gigabytes of swap space set up on this machine and only 2 gigabytes of actual physical RAM. So if you're working with a low-end machine like this, you will probably have to do this, or you will find that the build process fails. Once you are done, save and exit out of this file. So for me, that's escape:WQ. And if you head to the Yocto Project reference manual, you will find that there's a section on images. When you call BitBake, you will need to give it a specific image to build. Here's a list of supported images that you tell BitBake to build against, and it runs that specific recipe to produce a variety of packages and configurations. We're going to build Core Image Minimal. This is just a bare bones Linux image that has pretty much nothing in it other than a command line and a mostly empty root file system. There are other images where you can add things like software development kits, a real-time kernel, some graphical interface stuff, a Weston image, an X11 image if you want some graphical interface, and so on. So feel free to look through these, and you can also look at your vendor documentation to see if the vendor also provides recipes for different images. But for now, we are going to pick Image Core Minimal. Prior to doing that, if you'd like to make changes to your kernel, you can run bitbake-c menu config virtual/kernel and wait just a moment while it pulls up the menu config. The first time you run bitbake and it starts to read in the files and configuration that you have set, it will take a while to parse this. One of the really slick things about Yocto is that it tries to remember what it's done previously, so if it's already parsed some of the files and configurations that you have created, it doesn't need to parse them again. So even though this is saying it's going to take 10 minutes, it will only take 10 minutes the first time I run it, unless I redo the entire build process. Additionally, you will also find that even the build process is done so in stages. So if you make a few changes after you've completed the first build process, the build process will be much faster the second and third time. This is one of the big advantages of Yocto. If you make minor changes to the kernel or drivers and you try to tweak some things, the subsequent building does not take nearly as long. And that's one of the big reasons to use Yocto over something like Buildroot. Once BitBake finishes parsing all of the metadata, you should be presented with this configuration menu. Feel free to take a look at some of the things that are available for you, like some of the kernel features that you can turn on or turn off. Additionally, you have things like power management and drivers you can enable and disable, but we will actually leave all of this at the default for now. We can come back to this later if we need to enable certain things in our specific distribution. So just select Exit for now and say no to save the configuration. At this point, we're ready to build the actual image. So just say bitbake core image minimal and press enter. All of the metadata parsing should be completed, so that should be pretty quick. However, the compilation process will still take a few hours. It took 5 to 6 hours for my first run, so just be patient with this. You can let it run overnight, for example. If you can, periodically check the output and carefully read any error messages that you might see. For example, if it complains that you're missing a .h file, you'll probably need to install some package using something like Aptitude. The good news is that if you need to rerun this process, it will pick up where it left off. One of the big advantages of Yocto is that it builds in stages and layers, so that if you make tweaks to one of those layers, it doesn't rebuild all of the others, and it just rebuilds the ones that are needed and packages everything up for you, so subsequent runs will be faster. After a very long time, a number of hours, at least 5 or 6 for me, the compilation process finished. You should see an output like this saying everything is done. Hopefully you don't have any errors. There is a warning message here for me, but this looks like it should be okay for what we're trying to do. If you want to clean your build, you can enter bitbake-c clean all core image minimal. This will only remove the output images that you created. This is a good way to start over without having to recompile all the intermediate steps. However, if you want to remove all the intermediate steps and really start over from the beginning, what you'll notice is that all of the output is put into this temp or TMP folder. So all you would need to do is remove that temp folder, and that would allow you to start over from the very, very beginning. However, we're not going to do that, and instead, we are going to peek into that temp folder and find where the images were created. So inside temp, we want to go to deploy. In deploy, you should see a folder named images, and then depending on the vendor you're using, this folder might be different. For me, it's STM32MP1. Here is where you will find all of the output images. You will find things like ext4, which is a file system that you can do a byte-for-byte copy to a partition. You might find things like boot file systems, user file systems, root file systems, and then in some of the folders that are produced, you might find some information about how SD cards are laid out, such as this flash layout core image minimal. We will look at that in the next episode. FIP is part of the boot process, especially for trusted boot. Same with the ARM trusted firmware. We will be using these to create a boot chain in the next episode. A lot of these files can be confusing. In some instances, you might find a very simple SD card image file that you can just burn directly to an SD card like we did in the Buildroot episode. However, it does not seem that ST has provided us with such an easy option. So in the next episode, we're going to look at creating custom partitions on our SD card and finding out which of these files need to be copied over to those partitions in order to create a successful boot chain and then get a login prompt for Linux. I'm far from an expert in embedded Linux, as there are a lot of moving parts that I still don't fully understand. However, I hope that these videos can give you a good place to start. In the next episode, we will flash those image files onto an SD card and boot into our custom Linux distribution. Happy hacking!